Welcome back. Let's learn about tangent planes and normal lines. Alright, so we are now at the point in Calculus 3 where we can finally discuss how to find tangent planes to surfaces. And this is the natural extension to one of the main ideas or main focuses of Calculus 1, which was finding tangent lines to curves. Right, given a curve represented by a single variable function, we could find a tangent line at a point along that curve. And all that tangent line does is it takes the slope at that point along the curve and it extends it to be a line. And so when we wanted to find a tangent line at a point on a curve, we needed two things. For one, we needed the slope at that point on the curve, and we would find that by taking the derivative of the function that represents that curve and then evaluating that derivative at that specific point. And then of course the second thing we needed is the coordinates of that point where we want to find the tangent line. Okay, and so once we had the slope at that point and the coordinates of the point, we could put those values into the point slope formula and create the equation of the tangent line. And so that's what we did in Calculus 1. We could find tangent lines at a point on a curve represented by a single variable function, but now in Calculus 3, we are working with surfaces represented by a multivariable function where we want to find tangent planes at different points on the surface. All right, we've already talked about tangent lines, or finding the slope of tangent lines at a point on a surface, right? Partial derivatives will help us find the slope of the tangent line in the x or the y direction, and then directional derivatives, where we use unit vectors, help us find the slope in other directions. But when we're talking about a tangent plane at a point on a surface, we're talking about a plane that would contain all of those different tangent lines at that point on the surface. And so a tangent plane may look something like this. It is a plane that takes the three-dimensional slope, if you will, at that point on the surface and extends it forever to be a plane. But the question is, how do we find a tangent plane at a point on a surface? What do we need in order to find that? Well, if you think back to when we first learned about planes in 3D space, we learned that we describe planes using a normal vector, a vector that is perpendicular or orthogonal to that plane. And so in this case, that normal vector may look something like this, right? It's a vector that is normal to that plane, or essentially perpendicular or orthogonal. All of those words mean the same thing, but we need a vector like that along with a point to describe or create the equation of that plane. And so that's what we need. But how do we get it, right? Given a surface represented by a multivariable function and a specific point on that surface, how do we find a normal vector to the tangent plane at that point so that we can create the equation of that tangent plane? Well, in order to understand how we'll find this normal vector, what we first need to do is take a step back into two dimensions. Specifically, I want you to consider the scenario where we have a surface represented by this multivariable function, f of x, y equals z, with a specific level curve, f of x, y equals c, where c is a constant value. Okay, it's been a little while since we've last talked about level curves, but remember, all we're saying here is that we're taking our multivariable function and choosing a specific value for z, some constant c, and the result is an equation that gives us a level curve for that surface at that particular value of z. Okay, just imagine that you have a surface and you take a horizontal plane and cut it through at a particular value of z, which would be that constant of c. When you slice the plane through that surface, what you get is a level curve for that value of z. Okay, you start with a three-dimensional surface, but then the level curve is in two dimensions. It is a curve that we can graph in the xy plane. Okay, so that's what we're working with here. We're considering a surface with a specific level curve, and what we can do here is represent that level curve with a vector function, right? It's also been a little while since we've talked about vector functions, but remember that a vector function can be used to represent curves. The different components of the vector function come from the parametric equations that would represent that curve. Okay, so in this case, I'm going to let x be equal to a function f of t, and y will be equal to a function g of t. Those would be two parametric equations that we could use to represent this level curve in the xy plane, right? We don't need a third parametric equation for z because this is a 2D curve in the xy plane, so no z equation is necessary. But then using these two parametric equations, we could form a vector function. We'd have r of t is equal to f of t times I plus g of t times j. Okay, and so this should look familiar. We have worked with vector functions a lot previously in Calculus 3. It's just that in this case, we are using a vector function to represent a level curve. Now, before we go any further, I am going to change my notation a little bit here. I started out with f of t and g of t so that it would look familiar and you'd recognize it, because this is how we've worked with vector functions in the past. But to avoid any potential confusion with our different functions, since we've already used f for f of xy equals z, our multivariable function, I don't want to use f again, and so I'm just going to completely change the notation for x and y. Instead of having x equals f of t and y equals g of t, here's what I'm going to replace them with. This way there's no question about what we're working with. I'll let x be equal to x of t and y be equal to y of t. All right, so our vector function will have an x component of x of t and a y component of y of t. That will be the vector function that will represent this level curve. And then what we can do, using the components of this vector function, or using these parametric equations, is rewrite the function for our level curve. Right, we have f of xy is equal to some constant c. We could replace x and y in this function with what they are equal to in terms of the parameter t. And so we would have a function whose independent variable is t. Okay, so here's what that looks like. If we let x and y equal these parametric equations, then the function for our level curve could be rewritten like this. We'll have f of x of t, comma, y of t, and that would be equal to the constant value c. Okay, again, this is just a function that represents this level curve, but now it's in terms of the parameter t, which would be the independent variable for the function. And then what we can do here is take a derivative of this function, which now that the function is defined in this way, would require the use of the chain rule for multivariable functions, right? In this case, the function f is defined in terms of two intermediate variables, x and y, that are both defined in terms of one independent variable of t. Okay, you could draw out the derivative tree here for the chain rule. F has two intermediate variables of x and y, which are both defined in terms of that independent variable t. So if we take the derivative of both sides of this equation, we'll use the chain rule to take the derivative of f, and then the derivative of the constant c would be 0 because the derivative of all constants is 0. Okay, so let's use the chain rule here. We're going to have two terms. We'll have one term for this branch of the derivative tree and another term for this branch. And since we have a choice between x and y for the intermediate variables, going from f to x or from f to y will result in a partial derivative. So we will get the partial of f with respect to x multiplied by the derivative of x with respect to t, which would be a regular derivative because we have no choice here. X is only defined in terms of one independent variable. So you'd multiply by dx dt, and then we will add that to the partial derivative of f with respect to y. So I have the partial of f with respect to y multiplied by the derivative of y with respect to t. Again, that will be a regular derivative because y is only defined in terms of one independent variable. So we have dy dt. And those two terms will be equal to 0 because, again, the derivative of a constant c will be 0. Okay, and so now that we've done that, what's next? Where are we going with this? What's the point? Well, we're almost there. Just hang on for a little bit longer. What I want you to notice about this derivative is how this calculation, or the sum of these two terms, can be viewed as the result of a dot product, right? Remember that a dot product between two vectors is equal to the sum of the product of corresponding components. If you have two vectors in two dimensions, vector v and vector u, their dot product is the product of the x components plus the product of the y components. We could view this calculation as a dot product between two vectors, because in both of these terms, the x's and the y's match up, right? You have the partial of f with respect to x, and then the derivative of x with respect to t, and in this term you have the partial of f with respect to y, and then the derivative of y with respect to t. Okay, so you could view the partial derivatives as being the x and y components of one vector, and then these regular derivatives as being the x and y components of another vector. And so let's do that. Let's rewrite this calculation as a dot product between two vectors. One of the vectors will have an x component of the partial of f with respect to x, so that's multiplied by I, and that will be added to the y component, which will be the partial derivative of f with respect to y, so that will be multiplied by j, and you will take the dot product of that with another vector whose x and y components will be these two regular derivatives. So we have dx dt as the x component, and that will be added to dy dt, or the derivative of y with respect to t, times j, and that will still be equal to 0. Okay, now before we talk about why this dot product is significant, a couple changes I want to make here. First of all, let's use a different notation for the partial of f with respect to x and the partial of f with respect to y. Just to make things simpler, we'll have fx times I plus fy times j, and then we have dot this vector, but we could also rewrite the notation for these two derivatives, because really what these derivatives are just the derivatives of the two parametric equations that we defined earlier, right? dx dt would be the derivative of x of t, and dy dt would be the derivative of y of t. So we could rewrite those derivatives like this. We'd have x prime of t times I plus y prime of t times j, and that's still equal to 0. Okay, now we're almost there. We're almost at the point where we can make a very nice conclusion about something that will help us determine how to find the normal vector for a tangent plane to a surface at a point. But before we get there, notice what is interesting about these two vectors. Starting with the first one here, it's a vector where the x and y components are the partial derivatives with respect to x and y of the multivariable function. And so hopefully you recognize that, because that is a vector that we have just learned about in the previous lesson. That is the gradient vector for this multivariable function, right? And so we could rewrite it in that way. We can represent that vector with del f of xy, and we would take the dot product of that vector with this vector, which also represents something that we have learned about before. And what I mean by that is compare this vector to the vector function that we defined earlier. This vector function had x and y components of x of t and y of t, and this vector, which would be a vector function, has an x and y component of the same functions, but their derivatives. And so this vector right here is just the derivative of this vector function. Because remember, when you take the derivative of a vector function, you take a derivative of each component individually. So the derivative of r of t would be x prime of t times I plus y prime of t times j, the exact vector we have right here. So you can rewrite that vector with the vector function r prime of t, and that dot product is still equal to 0. But this right here is a very interesting result. What we have found is that the gradient vector for a multivariable function, dot product with the derivative of the vector function that represents a level curve for that function, is equal to 0. And so why is that significant? Well, remember what it means when the dot product between two vectors is equal to 0. When you take the dot product of two vectors and you get 0, that means that those two vectors are perpendicular or orthogonal. Okay, so this equation right here implies that the gradient del f of xy is perpendicular to the derivative of the vector function. And this is really cool because if you remember, we learned that the derivative of a vector function represents the tangent vector at any point along the curve that the vector function represents. And so if the gradient vector is perpendicular to the tangent vector, then that means that the gradient vector would have to be the normal vector, specifically the normal vector for a point on a level curve of a multivariable function. Okay, so to really drive this point home, here's what we're working with. The conclusion that we have just made is that since the gradient vector, del f of xy, and the derivative of the vector function, r prime of t, are perpendicular, and r prime of t is the tangent vector of the level curve, then the gradient vector would be the normal vector. And so if we were to look at a level curve, or at least a part of it, remember that we are representing a level curve with a vector function r of t, and we consider a particular point on that level curve, then the tangent vector would look something like this, right? This would be r prime of t, that's the tangent vector, and then the gradient vector, which would be perpendicular to that tangent vector, would look something like this. It would make a right angle with that tangent vector, meaning that the gradient vector, del f of xy, is the normal vector to that point on the level curve. And if you think about it, this should make sense. Remember in the previous lesson on the gradient vector that we learned that the gradient vector points to the steepest slope for the surface at a particular point, which we could view that as being the fastest way to travel up a surface. That path would actually be perpendicular to a level curve. For example, let's say we have a surface that sort of looks like a hill, and we draw out some level curves for that surface. The fastest way up this surface would be along the path perpendicular to a level curve. So if we're starting at the bottom of the surface with this level curve here, let's say we're at this point. At that point, what is the quickest way to move up the surface? Is it to go this way? No. Is it to go this way? No. It would be this way, right? The direction that is perpendicular to that point on the level curve. This direction would be the quickest way to move up the surface. And then when you get to the next level curve, you could look at another point, and the quickest way to travel up the surface, or the direction of the steepest slope, would not be this way or this way, but in a direction that is perpendicular to that point on the level curve. Okay, so this does make sense. Concluding that the gradient vector is the normal vector at a point on a level curve is consistent with how we have previously defined or understood the gradient vector. It's still a vector that points to the direction of the steepest slope on a surface at a point, but it just also happens to be the case that that vector would be normal or perpendicular to a point on a level curve for that surface. Okay, but we can't quite wrap things up just yet because so far we've only talked about level curves, right? We have determined that the gradient vector is the normal vector to a point on a level curve, but at the very beginning of this lesson, our goal is to find a normal vector to a point on a surface, not a curve. And so right now, we're working in one dimension lower than what we desire, but the good news is that this idea extends to more dimensions. Since we know that the gradient vector, del f of xy, is the normal to a level curve, f of xy equals c, then by extension, the gradient vector, del f of xyz, would be the normal to a level surface, f of xyz equals c. That is what we were looking for. In order to find a tangent plane at a point on a surface, we need a normal vector at a point on a surface, which is exactly what this describes here. Okay, so it can be a little confusing at first, but remember, a gradient vector is always one dimension less than the function you're finding that gradient for. So del f of xy could not be the normal vector at a point on a surface because this would be a two-dimensional vector. It's the gradient vector for a three-dimensional surface, which would be in 2 dimensions. That's why it's the normal to a level curve for the function. And so then the gradient vector of a function of 3 independent variables would be a 3D gradient vector. Okay, because the actual function, f of xyz, would represent a 4-dimensional shape that would have 3-dimensional level surfaces. So the gradient vector for that 4-dimensional shape is a 3D vector that is normal to a level surface where you have that multivariable function equal to some constant. Okay, so it's very important that you recognize that relationship between the gradient vector and a multivariable function. The gradient vector is always one dimension less, and we use that to our advantage to help us find a normal vector to a point on a surface. And so to sum everything up, here's what we can do. Starting with a 2-dimensional scenario, and then we'll take a look at what we're really interested in, which is the 3-dimensional scenario. But in 2 dimensions, you could find a normal line to a curve by using the gradient vector. You just have to work through the following 3 steps. You'll be given a curve, y equals f of x, and you want to view that curve as a function of 2 variables. Okay, what you could do is get all the x and y terms on one side of the equation so that you have terms of x and y equal to some constant, and then you could view that as a multivariable function. You could view that as a function f of xy equal to some constant, which would then represent a level curve for a surface. Okay, and so viewing it in this way allows you to then find a gradient vector for that surface, and then you want to evaluate it at the point where you want to find a normal line to the curve, and then that gradient vector is the normal vector at that point, and so it would have the slope that you need for the line. So you would take the y component of the gradient vector divided by the x component that will be the slope of that normal vector, and then you could use that slope with the point where you want to find the normal line and put them into the point slope formula, y minus y1 equals m times x minus x1, and that will give you the equation of the normal line at a point on a curve. Okay, so that's the 2D scenario. This isn't really what we're interested in here for Calculus 3. We will look at one example of this, but really the only reason I bring this up is so that you get a basic idea of what we're doing before we extend it into the third dimension, which is really what we're interested in doing here. Okay, and so speaking of which, here's how we can find the equation of a tangent plane and a normal line to a surface. We haven't really talked about normal lines up to this point, but this is also something that we can find using the gradient vector. And so you'll see that in just a second, but to start, the first step is to view your given surface as a function of three variables. Okay, so you'll be given some surface, z equals f of xy, where you want to find a tangent plane at a point on that surface. And to do that, what you have to do is view that function as a function of three variables. You want to get all the x, y, and z terms on one side of the equation so that it's equal to 0 or some constant, so that it's in this form. You have a function of x, y, and z equal to some constant c, which would represent a level surface. Okay, it's a level surface of the four-dimensional shape that would be represented by this function, but this specific level surface is the surface that you've been given where you want to find the tangent plane. Okay, I hope that makes sense. That's the connection here. But then once you view your function in this way, you can find the gradient vector, del f of x, y, z, and evaluate it at the point where you want to find the tangent plane, and that resulting vector is the normal vector at that point on the level surface. And so you can use the point that you've been given, as well as that normal vector, which is just the gradient vector, for f of x, y, z, which will have an x, y, and z component, which I'm representing with a, b, and c, that can then be used to form the equation of a plane. And so this should look familiar. We learned about this earlier in Calculus 3. This is what we use to set up the equation of a plane. A, b, and c are the x, y, and z components of the normal vector, which would be the gradient in this case. And then x1, y1, and z1 are the x, y, and z coordinates of the point where you want to find the tangent plane. Okay, so putting that all together and simplifying will give you the equation of the plane tangent to the point on the surface. And then also you can find a normal line at that point on the surface. Remember that to find a line in 3D space, you just need a vector and a point. And so in this case, if you use a vector that is normal to a point on a surface, then you can find the normal line at that point on the surface using the components of that normal vector along with the coordinates of the point. Okay, so you could set up the equation of that line using the symmetric equation. Again, this is something that we learned about earlier in Calculus 3. You take x minus the x coordinate of the point, divide by the x component of the normal vector, set that equal to y minus the y coordinate of the point, divided by the y component of the normal vector, and then set that equal to z minus the z coordinate of the point, and divide that by the z component of the normal vector. Okay, so that's how I would choose to set it up. I would use the symmetric equation for a line in 3D space, but if you wanted to, you could also use the parametric equations, which look like this. X would be equal to a times t plus the x coordinate, y equals b times t plus the y coordinate, and z equals c times t plus the z coordinate. That is valid to use as well, but I think in most cases it will be easier for you to set up the symmetric equation of a line in 3D space. Okay, so using the normal vector, which is the gradient vector, you can find the equation of a tangent plane and a normal line at a point on a surface. Okay, and of course all of this, as well as with the 2D scenario, is assuming that the gradient vector is not the zero vector. Okay, if it is the zero vector, this doesn't really work, but that pretty much will never be the case, so you don't have to worry about that too much. Alright, and so that's it. We now know how to find a tangent plane at a point on a surface. And so what we're going to do next is look at these different processes in action. We'll start with an example of a two-dimensional scenario where we want to find a normal line to a point on a curve, which will help introduce the process of what we're doing here, and then we'll extend it and look at a three-dimensional scenario, which again, that's the main focus. That's what we're really interested in. And so let's take a look at our first example. Hey, real quick, before we get to the next part of this lesson, if you find my videos here at JK Math to be helpful, then I'd like to invite you to join my membership site JK Math Plus, where you get access to many perks, including bonus content and my exclusive community. The bonus content includes dark mode versions of my videos, extra example problems, and more, while the community is a private space online where you can post questions, have discussions, and study together with me and other members. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out, as it's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the lesson. For this example, we want to find the normal and tangent line at the point on the curve. And we're given y equals sine x for the point pi divided by 3, the square root of 3 divided by 2. All right, so remember, the first thing we want to do here is view this single variable function that we've been given as a multivariable function, right? What we've been given here is our classic single variable function that we have worked with in Calculus 1, Calculus 2, and so on. Y is the dependent variable defined in terms of x. But what we want to do is get it in a form where we can view it as a multivariable function of two independent variables, that being x and y. So to do that, we need to get all the x and y terms over to one side of the equation. So in this case, to do that, I'll just subtract sine x from both sides of the equation. And that will give us y minus sine x is equal to 0. Okay, this is now in the form of a multivariable function, f of xy, equal to a constant c, which means that this represents a level curve of a 3D surface. So now that we're viewing it in this way, we can find the gradient vector for this function, which will be a vector that is normal to a point on that level curve. Okay, so let's find the gradient vector. Del f of xy will be equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j. So the partial derivative with respect to x of this function, ignoring the constant part, you're just looking at this right here, f of xy. Y would be a constant with respect to x, so just take a derivative of negative sine x, which will be negative cosine x. So this is equal to negative cosine x times I, plus the partial derivative with respect to y. Negative sine x is just a constant, so its derivative is 0, and then the derivative of y is 1. So you just get 1 times j. Okay, so the gradient vector is negative cosine x times I plus j. Now, what we have here is the gradient vector, but what it represents is a vector that is normal to this curve y equals sine x for any point. We can plug in the x and y coordinates of any point along this curve into this gradient vector, and we will get a vector that is normal to that point, meaning that it would be perpendicular to the tangent vector at that point. Okay, and so what we want to do is find the specific normal vector at this point that we've been given. So we want to evaluate the gradient vector at x equals pi divided by 3 and y equals the square root of 3 divided by 2. And in this case, the gradient vector doesn't have any y's in it, so we're just going to be plugging in pi divided by 3 in for this x, and cosine of pi divided by 3 is 1/2, so we get negative 1/2 I plus j. Okay, this is a specific normal vector at this point on this curve. And so now we're almost there. If we want to find the normal line at the point on the curve, what we want to do is take the slope from the normal vector and then use that with this point in the point slope formula to find the equation of that line. Okay, so from this vector, the y component is 1, the x component is negative 1/2. So the slope of the normal vector would be m is equal to the y component of 1 divided by the x component of negative 1/2. And that will give you negative 2. Okay, and just in case you're not following why that works, if I quickly sketch a graph of a 2D vector here, let's say we have a vector like this with a particular x coordinate and a particular y coordinate. That vector would have a slope of the rise over the run, so take the y coordinate divided by the x coordinate, and that will give you the slope of this vector, which could be used for the slope of a line. Okay, that vector and the line would have the same slope. In this case, that line would be the normal line, because the vector that we're using is the normal vector to that point on the curve. Okay, so now that we have the slope of the normal vector, we can find the equation of the normal line by using that value of m and the coordinates of our point. All right, so remember, the point slope formula is y minus y1 is equal to the slope times x minus x1, and the y coordinate is the square root of 3 divided by 2, the x coordinate is pi divided by 3, and the slope is negative 2. So we get y minus the square root of 3 divided by 2 is equal to negative 2 times x minus pi divided by 3, and then simplifying, I'm going to distribute negative 2 through this quantity, and then add the square root of 3 divided by 2 to both sides of the equation. So we solve for y and get y is equal to negative 2x plus 2 pi divided by 3 plus the square root of 3 divided by 2. All right, and that right there is the equation of the normal line. But notice that this problem does also want us to find the tangent line at the point on the curve, which is not too difficult because remember, the normal line would have to be perpendicular to the tangent line, meaning that they would have opposite slopes. This is something that you learn way before calculus, most likely in algebra. If you have the equation of one line and you want to find the equation of a line perpendicular to it at the same point, then what you do is you use the same point, but then use the opposite slope, which turns out to be the negative reciprocal of the slope. Okay, so you negate this slope, which would make it positive 2, take the reciprocal, so it's 1/2, and that will be the slope of our tangent line, which is perpendicular to the normal line. Okay, and so if it's been a while since you've done that, don't worry about it. This is just a one-off example showing you what you can do with the gradient vector for a two-dimensional curve. But what we get for the tangent line is y minus the square root of 3 divided by 2 equals that opposite slope of positive 1/2. Again, we negated this slope, took its reciprocal, and that will be the slope of the tangent line, which is perpendicular to the normal line. And then we have x minus pi divided by 3. And so again, simplifying, we get y is equal to 1/2 times x minus pi divided by 6 plus the square root of 3 divided by 2. I distributed 1/2 through this quantity and then added the square root of 3 divided by 2 to both sides of the equation to get this equation, which is the equation of the tangent line. Okay, and so if you were to look at the graph of the sine function, it looks something like this. You have a curve with this type of shape. The point that we're working with here, pi divided by 3 and the square root of 3 divided by 2 as the x and y coordinates, is somewhere about right here. And so the tangent line that we found would be a line like this, that's tangent to the curve at that point. And then the normal line would be a line that cuts through that point that's perpendicular to that tangent line. Okay, so if that's the tangent line, then this would be the normal line like that. Okay, just to give you a visual of what we found here or what we're working with. But the main idea that you want to take away here is that process of viewing the function as a level curve of a function that is 1 degree higher, and then you find the gradient of that function. We are going to reuse that idea in our next example, where we finally take a look at the three-dimensional scenario where we want to find a tangent plane at a point on a surface. And so let's take a look. For this example, we want to find the tangent plane and normal line at the point on the surface. And we've been given x squared plus y squared plus z squared equals 14 and the point 1, 2, 3. All right, so what we've been given here is a multivariable function that represents a surface in 3 dimensions. Specifically, this equation here represents a sphere, if you recognize the form of this equation. But what we want to do here is view it as a level surface of a 4-dimensional shape, okay? We actually don't have to change anything here. This is already in the form that we want. We have all the x, y, and z terms on one side of the equation equal to some constant. So it's already in the form of f of x, y, z is equal to c, where that constant is 14. Okay, so we could view these 3 terms as being a multivariable function of 3 independent variables. And by doing that, by treating this as a level surface of that function, we can find the gradient vector for that function, which will be the normal vector to any point on that level surface, which is the surface that we've been given here. Okay, so again, we're just viewing our given surface as a level surface of a 4-dimensional shape, because by doing that, that allows us to find a gradient vector in 3 dimensions that will be normal to any point on that surface, so that we can find a tangent plane as well as a normal line. Okay, so let's find that gradient vector. The gradient, or del f of x, y, z, will be equal to the partial derivative with respect to x times I plus the partial derivative with respect to y times j plus the partial derivative with respect to z times k. All right, so looking at this function here, if we're going to take a partial with respect to x, there's only one x term, so the derivative of these two terms is 0. So just take the derivative of x squared, and you'll get 2x times I. And then the partial derivative with respect to y is just going to be 2y, because x squared and z squared are constants with respect to y. The derivatives are 0, so just take the derivative of y squared, and you get 2y times j, and then add that to the partial derivative of z, which will be 2z, because z squared is the only term that's in terms of z. X squared and y squared are both constants with respect to z, so their derivatives are 0, and then the derivative of z squared is 2z. So you have 2z times k. All right, so this right here is the gradient vector for this function, but it also represents the normal vector for every level surface at any point for this function f of x, y, z. But as soon as we evaluate it at this point, then we will be looking at the specific normal vector at this point on this specific level surface. Okay, so let's find the specific normal vector to this level surface at this point. We just have to plug in those coordinates into the gradient vector. So doing that here, we'll have del f of 1, 2, 3, and that will be equal to 2 times 1, which is 2. So we get 2i plus 2 times y, so 2 times 2, which is 4, times j, plus 2 times z, which will be 2 times 3, and that is 6. So we have 6k. All right, so this is the specific normal vector to this level surface at this point. And now that we have that, we can very quickly find both the tangent plane and the normal line at this point on the surface. And so let's set those up. Let's start with the tangent plane. This is our setup for the equation of a plane, where a, b, and c are the components of the normal vector. And so in this case, our gradient vector is the normal vector. That's what we want to use here. These components, so we'll have 2 times x minus the x coordinate of 1 plus b, which would be 4. That's the y component of the normal vector. And that's multiplied by y minus the y coordinate of 2. And then we have plus c, the z component of the normal vector, which is 6. So we have 6 times z minus the z coordinate of 3, and that's equal to 0. And so simplifying, distribute 2, 4, and 6 through their respective quantities, and you get 2x minus 2 plus 4y minus 8 plus 6z minus 18 equals 0. All right, and then just to make it look nicer, move all the constants over to the other side of the equation. So we have negative 2 plus negative 8, which is negative 10, plus negative 18, which is negative 28. So if you move that to the other side of the equation, you get positive 28. So altogether, the equation of the tangent plane is 2x plus 4y plus 6z is equal to 28. That would be the equation of the tangent plane. And if you wanted to, you could simplify it further. All of these terms have a common factor of 2, so you could factor that out, divide both sides of the equation by 2. And if you did that, another possible answer that you could get that looks nicer is x plus 2y plus 3z equals 14. Okay, but you don't have to do that. That's completely optional. I just thought I'd show you that in case you were wondering if you could do it. You can, but generally, I'll just leave it like this. And so that's the tangent plane. But now what about the normal line? Well, we just have to set up this symmetric equation of a line using the components of the normal vector, which again is our gradient. So doing that here, we have x minus the x coordinate of 1 divided by a, which is 2, and that will be equal to y minus the y coordinate of 2 divided by b, which is 4, and that's equal to z minus the z coordinate of 3 divided by c, which is 6. Okay, again, a, b, and c are just based on the x, y, and z components of that normal vector. And so this right here is the symmetric equation of the normal line to this point on the surface, just like this is the equation of the tangent plane at this point on the surface. Okay, and so hopefully you can see that this process is fairly straightforward. You just want to view your given surface as a level surface to a four-dimensional shape, which then you can find the gradient vector of, which will be the normal vector for every level surface at any point for that function. And so there will be more examples of finding tangent planes and normal lines in my examples video for this topic. But before we close out this lesson, there's one more thing that I want to talk about, and that is the angle of inclination for a tangent plane. We can find the angle between a tangent plane and the xy plane using the gradient vector. And that angle that we find is known as the angle of inclination. It tells you the incline for that plane. And this isn't entirely new because earlier in Calculus 3, we did learn how to find the angle between two planes. That looks like this. If you have two planes that intersect and you want to find the angle between them, the angle is simply the angle between their normal vectors. And so we use a formula from even earlier in Calculus 3 for finding the angle between two vectors. Cosine of that angle is equal to the dot product of those two vectors. So in this case, the dot product of the two normal vectors, but the absolute value of that dot product. And then that's divided by the product of those vectors' magnitudes. Okay, so in the case where we're working with a tangent plane and the xy plane, that looks like this. Let's just say that this plane right here is a plane that is tangent to some point on some surface. I sort of have this shadow drawn here that it would make in the xy plane to help you visualize what this looks like. But then the angle that we're interested in is the angle between that plane and the xy plane. And so to find that angle, we need the normal vectors of those two planes. For the tangent plane, the normal vector would be the gradient vector, right? Vector n would be equal to the gradient of f of x, y, z. And then the normal vector for the xy plane would just be the standard unit vector k, right? The standard unit vector for the z direction. The unit vector k would be perpendicular or orthogonal to the xy plane. So you could draw that anywhere within the xy plane. I'm just going to draw it right here. That would be vector k. Technically, you would put it at the origin, but I'm just changing where its initial point is. I'm putting it right here at the same point where this normal vector is being drawn from on this plane. And so essentially what we're saying here is that the angle between those two normal vectors is the same as the angle of inclination for the tangent plane and the xy plane. Okay, again, the normal vector for the tangent plane is the gradient vector, and the normal vector for the xy plane is the standard unit vector k. So, setting up this formula, we get cosine of that angle of inclination is equal to the absolute value of the dot product between those two normal vectors. So we have the gradient of f of x, y, z dot vector k, and then that's divided by the product of their magnitudes. So we have the magnitude of del f of x, y, z, and then that's multiplied by the magnitude of vector k. But remember, vector k is a standard unit vector, so its magnitude is just 1. So our final formula here would be cosine of the angle of inclination is equal to the absolute value of the gradient vector dot product with vector k, and that's divided by the magnitude of the gradient vector. So the magnitude of del f of x, y, z. Okay, so that right there is the formula to find the angle of inclination between a tangent plane and the xy plane. You want to set up this calculation and then solve for the angle theta by using the inverse cosine function. And do notice that when you do this dot product between the gradient and vector k, that the first two terms will just be 0 because the x and y components of k are 0. So really you're just going to be multiplying 1 by the z component of the gradient vector. Okay, so you could even simplify this further, but I'm going to leave the formula like this. And to close out this lesson, I want to take a look at one example where we use this formula. For this example, we want to find the angle of inclination of the tangent plane to the surface at the given point. And we have 3x squared plus 2y squared minus z is equal to 15, and then the point 225. Okay, so we've been given a surface here that's already in the form that we need to find the normal vector of the tangent plane at any point on it, right? We need it in that form of f of x, y, z is equal to some constant c so that we can view it as a level surface of a four-dimensional shape. And that is what we have here. The x, y, and z terms are all on one side, and then we have a constant on the other side of the equal sign. So we're good to go. We can treat these three terms as a multivariable function of three independent variables, and so we can find the gradient vector, which would be the normal vector for the tangent plane, which is what we need to calculate the angle between that tangent plane and the xy plane, which is the angle of inclination. Okay, so let's find the gradient vector here. del f of x, y, z will be equal to an x component that is the partial derivative with respect to x. So in this case, there's only one term in terms of x, so just take the derivative of that. The other two terms would have a derivative of 0 with respect to x. So we get 6x to the first power times I, right? That would be the derivative of 3x squared. Then we'll add that to the partial derivative with respect to y. And so again, 3x squared negative z are constants with respect to y, so the derivatives are 0. Just take the derivative of 2y squared, and you get 4y to the first power, and that's multiplied by j. And then for the z component, take a partial derivative with respect to z, which will just give you negative 1. The derivative of negative z is negative 1. And these two other terms would be constants with respect to z, so their derivatives are 0. So we have minus k as the last term for that gradient vector. Okay, and then what we want to do is find the specific gradient vector, or the specific tangent vector at this point, and then that will give us the specific normal vector for the tangent plane at that point on the surface. And so let's evaluate it at the point 225. We'll have the gradient of f of 225 is equal to 6 times 2, which is 12. So we have 12i plus 4 times y, so 4 times 2, which is 8. So we have 8j minus k. Okay, there's nothing for z. We don't have to plug in 5 for anything. But now we have that gradient vector, which is all that we need to find this angle of inclination. We already know what k is. I can write it down. We know that vector k is equal to 0i plus 0j plus 1k, or just plus k. Those are the components of vector k by definition. And so let's set up the formula here. We'll have cosine of the angle of inclination is equal to the absolute value of the gradient of f of 2, 2, 5 dot vector k, and that will be divided by the magnitude of that gradient vector. So we have the magnitude of the gradient of f of 2, 2, 5, and that's it. Okay, so continuing over here, we'll have cosine theta is equal to the absolute value of this dot product. So take the sum of the product of corresponding components. 12 times 0 is 0, plus 8 times 0 is 0, plus negative 1 times 1 gives you negative 1. I'm just going to write it like that. And then we're dividing by the magnitude of that gradient vector. So take the square root of the sum of the components squared, which I will write out. We have 12 squared plus 8 squared plus negative 1 squared. The absolute value of negative 1 is 1. And then 12 squared is 144. 8 squared is 64, and negative 1 squared is 1. Add those numbers together, and you get the square root of 209. So we have cosine theta is equal to 1 divided by the square root of 209, which means our last step here to solve for theta is to use the inverse cosine function to cancel out with this cosine, giving us theta is equal to arc cosine of 1 divided by the square root of 209. And if you put that into a calculator, depending what mode you have it in, you might get a value of radians. But I think in this case it makes more sense to work in degrees, because you're going to get a nasty decimal in terms of radians that's hard to make sense of. But assuming you get your answer in degrees, theta will be equal to about 86.03 degrees. And I did round that off. That's not an exact value, but it's good enough for what we're trying to do here. That is the angle of inclination for the tangent plane at this point on this surface. Okay, it's the angle between that tangent plane and the xy plane. And so with that, that is it for this lesson. But if you want to get some more practice finding tangent planes and normal lines, feel free to check out my examples video for this topic that'll have linked here on the screen. If you have any questions, please let me know in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.